probably know of methamphetamine as an illicit recreational drug. At the molecular level, the main psychoactive component looks like this. What you might not know is that the mirror image molecule is perfectly legal in many countries, where it serves as a nasal decongestant. Escitalopram is an effective antidepressant. The mirror image molecule is not. This form of ethambutol is used to treat tuberculosis. The mirror image molecule can cause eye damage, often manifesting as some form of colour blindness. Molecules like these that come in two distinct mirror image forms, known as enantiomers, are said to be chiral and have chirality, terminology introduced by Lord Kelvin, deriving from the Greek word for hand. Here to tell us more about molecular chirality is a world-leading authority, Professor Lawrence Barron.
The subject of chirality at first arose through an experimental discovery by French scientists in the early years of the 19th century. They discovered that if you pass linearly polarized light through a quartz crystal, for example, the plane of polarization rotates through a certain angle. Then another form of quartz was discovered which gave an equal and opposite sense of optical rotation. Now that was fine. People could conceive of some sort of asymmetric structure in the crystal, some sort of helical arrangement or something. But then optical rotation was discovered in organic liquids like turpentine. Well, that was a big puzzle. It's a fluid, it's uniform. Where's the structure there? Well, this mystery was resolved very dramatically by Louis Pasteur in 1846. He was working with tartaric acid. If you dissolve it in water, it shows optical rotation like turpentine. But there was an unusual form of tartaric acid called paratartaric acid, which was found in the brewing industry. When you dissolved it in water, it gave no optical rotation. It was optically inactive. That was a great puzzle. But Pasteur was a very, very careful scientist, and he examined the crystals of paratartaric acid through a microscope, and he noticed that there were two types there which were mirror images of each other. He carefully separated them, looking through the microscope, into two piles. When he dissolved the two separately in water, to his great delight, he found that one lot gave optical rotation one way, the other lot gave opposite optical rotation. Well, this was a tremendous discovery. What it showed was that this handedness resided in the individual molecules. One could start to conceive the structure of these incredibly tiny objects. People had to start thinking of molecules in 3 dimensions. Chirality is central to the modern pharmaceutical industry. Many drug molecules are chiral, but the two mirror image enantiomers often have very different physiological effects. Usually one of them has the desired pharmaceutical effect. The other, it's either weaker or does nothing, or it can be harmful.
This paradigm emerged in the wake of a tragedy. The late 1950s and early 1960s saw a surge in miscarriages and birth defects. The cause? Thalidomide, a sedative, developed at Chemie Grunenthal under a known Nazi war criminal and aggressively marketed to pregnant women as a remedy for morning sickness.
Thalidomide is a chiral drug. Only one of the two forms has the required sedative effect. The other is teratogenic, that is, produces birth defects.
The thalidomide tragedy sparked an overhaul of regulations and ultimately helped bring molecular chirality to the forefront of pharmaceutical research. In the 1960s, there were relatively few techniques for chiral analysis. Optical rotation, discovered over a century before, remained widely used, but often proved inadequate even for basic tasks. One such task is the assignment of absolute configuration.
Say you've synthesized a new chiral molecule that's a drug candidate. You know it's optically active, it shows, say, optical rotation. But how do you know whether it's, say, the right or the left-handed form? It's a very subtle problem to relate that, say, to the sign of the optical rotation angle.
There was a need for something better. As a young man, Professor Barron pioneered a new technique that would help revolutionize chiral analysis.
It's called Raman optical activity. You have a laser beam passing through a liquid or solution sample. As a photon bounces off the molecule, it can leave the molecule in an excited vibrational state. The frequency shift of the photon is characteristic of that particular vibrational frequency of the molecule. You measure the light scattered intensity in right circularly polarized incident light, measure it in left, and there will be a very tiny difference that reflects the three-dimensional structure of the molecule, including its absolute handedness. To interpret it, you use quantum chemical simulations. If all the signs agree, you would literally stake your life on knowing the absolute configuration.
Raman optical activity has been applied to a wealth of problems, from the determination of absolute configuration and enantiomeric excess to the conformational analysis of large biomolecules in aqueous solution and even the molecular structure of intact viruses. It is a cornerstone of modern chiral analysis. You might be wondering why differences like these occur.
The chemistry of life is what we call homochiral. Polypeptides and proteins are made up of amino acids, but you only ever find the L version within a living system. Similarly, in nucleic acids, the sugars you find are always the D form of the sugar.
In much the same way a glove discriminates between left and right hands, the homochiral chemistry of life discriminates between the enantiomers of a chiral molecule.
It's like in engineering. Once you have a convention for right-handed bolts, you have to have right-handed nuts.
The mirror image forms of some large biomolecules can now be synthesized in the laboratory and might prove revolutionary for information storage and as medicines. Entire mirror organisms might one day be synthesized, perhaps even mirror people. Such a person would find correlations like this reversed. Some welcome the possibility of mirror organisms. A mirror person might be immune to existing microbes and viruses. Others warned that mirror organisms could be dangerous. In one hypothetical scenario, a single droplet of mirror cyanobacteria finds its way into the ocean. Free of natural enemies, the mirror cyanobacteria multiply, and multiply, and multiply, taking over the base of the food chain. The mirror sugars produced by the mirror cyanobacteria cannot be digested by higher order life forms, causing the ecosystem as we know it to collapse. The mirror cyanobacteria continue to thrive, drawing down immense quantities of carbon dioxide from the atmosphere. Temperatures drop dramatically, ushering in a new ice age. All in all, an evolutionary reset.
Homochirality is an important theme in the search for life on other worlds. Assuming extraterrestrial life is based on complex organic chemistry in aqueous media like life on Earth, it has to be homochiral. Looking, say, for life on Mars, if there's some molecular residues of extinct life, there'll be amino acids there. If you can recover these amino acids, and if there's a big excess of, say, the L form over the D form, that would be very good evidence that those molecules are of biological origin.
Martian rock, soil and atmosphere samples are currently being cached by NASA's Perseverance rover. A future mission will hopefully return the samples to Earth, where they can be analysed for biosignatures, including molecular homochirality. This endocrinone molecule is a diuretic and can cause gout. Its mirror image can help prevent gout. The R enantiomer of carvone smells of spearmint. The S enantiomer smells of caraway. This enantiomer of olein acts as a sex pheromone on male olive fruit flies. The other enantiomer acts on females. The R enantiomer of mecoprop kills weeds. The S enantiomer lacks herbicidal activity. This enantiomer of promethazine is an effective antihistamine. The other enantiomer is also an effective antihistamine. Aspartame tastes 200 times sweeter than table sugar. The mirror image molecule tastes bitter. These galaxolide molecules have powerful musky scents. Their mirror images do not. Betulin gives silver birch trees their white colour and has anti-cancer properties. The mirror image molecule has not yet been investigated.